Black holes are among the most fascinating objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine a place where the fabric of space and time is bent to its absolute limit. This is the reality of a black hole. Black holes form when massive stars die. Stars are giant balls of gas held together by their own gravity. They produce energy through nuclear fusion at their cores. This outward pressure from fusion balances the inward pull of gravity. However, this delicate balance cannot last forever. When a star runs out of fuel, gravity takes over. The star's core collapses in on itself. This collapse is incredibly violent and energetic. If the star is massive enough, at least 10 times the mass of our Sun, the core will collapse into an infinitely small point. This point is called a singularity. It marks the birth of a black hole. Surrounding the black hole singularity is an invisible boundary called the event horizon. This boundary is not a physical surface, but a point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. Think of the event horizon as a waterfall. Imagine a raft approaching the edge. Once the raft goes over the edge, it is impossible for it to climb back up the falling water. Similarly, anything that crosses the event horizon is destined to fall into the singularity. The event horizon is determined by the black hole's mass. A more massive black hole has a larger event horizon. For example, if our Sun were to become a black hole, its event horizon would have a radius of only 3 kilometers. The event horizon acts as a shield, hiding the singularity from our view. We cannot see what happens inside a black hole because no light can escape to reach our telescopes. The intense gravity near a black hole warps the fabric of space-time, creating a region where the usual rules of physics seem to bend. This warping has bizarre and fascinating effects on light passing close to, but not crossing, the event horizon, making it appear to curve and twist in unexpected ways. Imagine the universe as a giant rubber sheet, a flexible surface that can be stretched and deformed. A black hole would be like a heavy bowling ball placed on the sheet, creating a significant dip. The bowling ball would cause a deep depression, distorting the sheet around it, much like how a black hole distorts space-time. Similarly, a black hole's gravity warps the fabric of space-time, causing light to bend and curve around it, creating a lensing effect. This bending of light is responsible for some of the strange visual effects near a black hole, making objects appear distorted. One such effect is gravitational lensing, where the black hole acts like a magnifying glass. As light passes near a black hole, its path is bent, altering its trajectory significantly. This bending can magnify and distort the images of objects located behind the black hole, creating a surreal view. It's like looking through a cosmic magnifying glass, where everything appears larger and more distorted. Another intriguing effect is the photon sphere, a region where light is trapped in orbits. This is a region surrounding the black hole where gravity is so strong that light is forced to travel in orbits, unable to escape. Imagine a beam of light getting trapped in a circular path around the black hole, endlessly circling it. Imagine falling feet first towards a black hole. As you approach the event horizon, the gravitational pull on your feet would be much stronger than the pull on your head. This difference in gravitational force is called a tidal force. Tidal forces would stretch your body out like a strand of spaghetti. This process, aptly named spaghettification, is an inevitable consequence of approaching a black hole. As you fall closer, the tidal forces would become increasingly extreme. Your body would be stretched thinner and thinner, eventually being ripped apart into a stream of atoms. These atoms would then be drawn into the black hole's singularity. Spaghettification is a rather gruesome thought, but it highlights the incredible power of a black hole's gravity. Section 5. Journey to Infinity, Approaching the Singularity. The singularity at the center of a black hole is a point of infinite density and zero volume. It is a region where the gravitational pull is so intense that not even light can escape. It is a place where our current understanding of physics breaks down. The known laws of nature no longer apply, and the equations that describe the universe fail. As you approach the singularity, the curvature of space-time becomes infinite. This means that space and time are distorted beyond recognition. Time itself would slow down for you relative to an observer far away. This phenomenon is known as gravitational time dilation. This effect, known as time dilation, is a consequence of Einstein's theory of general relativity. It illustrates how gravity can influence the passage of time. If you could somehow survive the journey to the singularity, you would witness the entire future of the universe unfold before your eyes. Every moment from now until the end of time would pass in an instant. However, reaching the singularity is impossible for any observer outside the black hole. The immense gravitational forces would tear apart any matter long before it reached the core. This is because the singularity is hidden behind the event horizon, which acts as a one-way membrane. Once crossed, escape is impossible. Once you cross the event horizon, there is no turning back. The gravitational pull becomes inescapable, drawing everything inward. The singularity represents the ultimate unknown in our universe. It is a frontier that challenges our understanding of reality. It is a place where the laws of physics as we know them cease to exist. The mysteries of the singularity continue to intrigue and baffle scientists. Section 6. Cosmic fingerprints, properties of black holes. Black holes may seem like simple objects, but they possess unique and fascinating properties. According to our current understanding, black holes are characterized by only 3 observable properties: mass, spin, and electric charge. The mass of a black hole determines its size and gravitational pull. The spin of a black hole refers to its angular momentum, a measure of how fast it is rotating. The electric charge of a black hole is a measure of its net electrical charge. Remarkably, all other information about the matter that formed the black hole is lost once it collapses beyond the event horizon. This concept is often referred to as the no-hair theorem. Imagine a black hole as a cosmic shredder. It doesn't matter what you throw into the shredder, all that remains is the same shredded material. Section 7. Whirling giants, rotating black holes, and the ergosphere. While all black holes are thought to rotate to some degree, some spin incredibly fast, approaching the speed of light. These rapidly rotating black holes are particularly interesting because their rotation affects the space-time around them in a unique way. Around a rotating black hole, there is a region called the ergosphere. This region lies outside the event horizon. Within the ergosphere, space-time itself is dragged along with the black hole's rotation. Imagine a boat caught in a whirlpool. The water's rotation forces the boat to circle around, even if it tries to move in a straight line. Similarly, objects within the ergosphere are forced to rotate with the black hole. The ergosphere has some intriguing consequences. For example, it is theoretically possible to extract energy from a rotating black hole by utilizing the energy stored within the ergosphere. Section 8. A quantum whisper, Hawking radiation and black hole evaporation. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery about black holes. He showed that black holes are not entirely black after all. Due to quantum mechanical effects near the event horizon, black holes can actually emit a faint thermal radiation. This radiation, known as Hawking radiation, arises from the creation of virtual particle-antiparticle pairs near the event horizon. Sometimes one particle falls into the black hole while the other escapes into space. This escaping particle carries away a tiny amount of the black hole's energy. Over vast timescales, much longer than the current age of the universe, Hawking radiation can cause a black hole to slowly lose mass and eventually evaporate completely. However, for typical astrophysical black holes, the rate of evaporation is incredibly slow. Section 9. Uncharted territory, lingering mysteries of black holes. Despite decades of research, black holes remain some of the most enigmatic objects in the universe. These cosmic phenomena challenge our understanding of physics and continue to intrigue scientists and astronomers alike. While we have made significant progress in understanding their properties and behavior, many mysteries still surround these cosmic titans. The more we learn, the more questions arise, pushing the boundaries of our knowledge. One of the biggest unanswered questions is what happens to information that falls into a black hole. This paradox has puzzled scientists for decades and remains one of the most debated topics in theoretical physics. According to quantum mechanics, Information cannot be destroyed. This principle is fundamental to our understanding of the universe at the smallest scales. However, the classical picture of black holes suggests that all information about infalling matter is lost forever. This contradiction between quantum mechanics and general relativity is known as the information paradox. Another mystery is the nature of the singularity at the heart of a black hole. This point of infinite density and gravity defies our current understanding of physics. Our current theories of physics break down at the singularity, suggesting that we need a more complete theory of gravity to fully understand these extreme environments. This quest for a unified theory continues to drive much of modern physics research. Furthermore, the role of black holes in the evolution of galaxies is still an active area of research. These massive objects are thought to influence the formation and growth of galaxies in profound ways. Astronomers are working to understand how supermassive black holes at the centers of galaxies influence the formation and growth of their host galaxies. This relationship is crucial for understanding the life cycle of galaxies. The study of black holes pushes the boundaries of our understanding of the universe. Each discovery brings us closer to unraveling the secrets of these fascinating objects. As we continue to explore these cosmic mysteries, we can expect to uncover even more astonishing insights into the nature of space, time, and gravity. The journey to understand black holes is far from over, and the future holds exciting possibilities.